Hey there! Do any of you know what this is I'm showing you? No? Well, that's okay. This is called a magnetic monopole, and we're going to tell you all about it.
First, let's start with some background knowledge. Here is a bar magnet that has two ends, one south and the other north. Magnets like these are called magnetic dipoles because they have two poles. If we had two magnets like that, then their like poles would repel each other, while their other poles would attract. Now picture a big knife coming and splitting the magnet in half.
Now, you may be thinking, oh, that's simple. There's two ends, one north and one south. However, it's a bit more complicated than that. Here, let me show you. Each side gets more magnets whenever it's split apart. So each side has its own north and south end and is still a dipole.
Awesome, right? Let's zoom in on one of the split magnets and see what's going on. Here we see there's a domain that has a bunch more magnets inside of it, and they all line up.
So how about we zoom in even more? If we do that, we will see that each magnet inside of the domain has its own north and south end. So what if we zoom all the way down to fundamental constituents of matter, elementary particles like electrons and protons? Will they still behave like dipoles?
Yes, materials like this bar magnet are magnetic because electrons in their atoms are tiny little magnetic dipoles, meaning that even elementary particles have both north and south pole.
Does this mean that magnetic monopoles do not exist?
There are good reasons for magnetic monopoles to exist. For example, it was known for a long time that all electric charge is quantized. In 1931, famous physicist Paul Dirac showed that quantization of charge can be explained if at least one magnetic monopole existed in the universe. Magnetic monopoles are also predicted by physics theories that are trying to unify all known forces, the grand unified theories.
That's why physicists have been searching for magnetic monopoles ever since, in different materials here on Earth, in cosmic rays, and even in moon rocks, but none have been found so far.
Can physicists create magnetic monopoles themselves?
They're trying to. Magnetic monopoles expected to have a large mass, and Einstein has taught us that any large mass takes a lot of energy. So for a physicist to create this in a lab, a big machine would be needed.
What about the Large Hadron Collider that has recently been constructed in Geneva, Switzerland? Can it be used to search for magnetic monopoles?
Yes, LHC is the largest accelerator in the world, and physicists have recently started trying to produce magnetic monopoles there. In fact, a team at the University of Alabama works with physicists from all over the world attempting to prove the idea that a single magnetic monopole exists within the framework of quantum mechanics.
Cool. How do they do that?
They accelerate particles and smash them together, and then look at the fragments of these collisions for signs of new particles.
There are 10 different experiments now at LHC. The one that looks for monopoles is called METAL. It is different from others because it uses passive detectors involving no gas and no moving parts. It does make records, however, that are permanent so they can be looked at later to discover new physics.
The main metals detector itself works like a camera that is sensitive specifically to new particles that look like magnetic monopoles.
Metal also has a detector that can trap magnetic monopoles, so they can be studied later. So overall, the metal experiment can detect monopoles with higher charges and mass compared to other experiments.
The take-home message is that the team at the University of Alabama are trying to prove that the North Pole can exist without the South Pole,
Or the South Pole can exist without the North.